Okay, so let's go over your quiz. This was a take-home, so there are no bonus points, but you still have to email me your score, or you can walk up and tell me, but emailing would be easy, and then I've got a record of it, and then you get your 1 point when you email me your score. So on the front, you had this chart, and the first question was, what's the normal boiling point of mercury? To do this, you just had to look at where the mercury line crosses atmospheric, and I made a crooked line there. Anyway, if you draw that down, it's clearly not 350. It is above 350. The answer I have is approximately 360 degrees. If you put 350 on a test, I'd probably mark it wrong because it's clearly more than 350. And we talked a little bit yesterday about the sort of dividing that space visually into halves, because you're best at dividing visually into halves. You're not great at dividing into quarters or eighths or anything else. If you're separating a mixture of N-octane and ethanol, what temperature would you have to heat it to get all the ethanol vaporized but none of the N-octane? So the number that I have written on my paper is about 100. Now, is that the only answer? No, it is not. It is not the only answer, and I didn't even draw that line straight. If you look at the line for ethanol, the normal boiling point of ethanol, and we said this the other day, normal boiling point of ethanol is around 75 or 80 degrees. N-octane, I mean, this is actually a nice, if you had to do a distillation, this would be a nice one to pick. N-octane is about 125 degrees. So you've got a very wide range. The other thing that I wrote sort of in the margin of mine, my answer for number one, I had 360 Celsius. For number two, I had about 100 Celsius, and then I made a note. Temp greater than 85 Celsius, that looks like an 88. 85 Celsius, less than 110 Celsius. So that's another way to handle it, is to write sort of an expression for, like, hey, it has to be it has to be hotter than this. It shouldn't be this hot. Well, we talked about in the other class a little bit with that question, and I like the distillation questions. If you are somebody who is going on in chemistry, if you're going to take especially organic chemistries, this is a way to purify the products of a reaction, is a distillation, running it through a distillation apparatus. Of course, the closer together the boiling points of your two substances are, the harder it is. And if, now are you going to have some, in this case, N-octane in with that ethanol when you recondense it? Yeah, you will. And you basically keep running it through a distillation apparatus until you're able to pull all of the other stuff out. The less of it you have the first time, the better. So the lower you can keep that temperature, the better, but you want to make absolutely certain that all the ethanol is gone. So you just really have to get it up above the boiling point of ethanol. Think about using an apparatus like that to separate two compounds. Where does it not really matter if you get everything out? Where does it really, really matter a lot? Pharmaceuticals are a huge one, where it matters tremendously, because impurities in pharmaceuticals kill. People are taking chemicals into their body that have biological action. If there are unintended chemicals in there, it can be really, really bad. So number 3, and going back to our graph, we're talking about at 5,000 feet above sea level, atmospheric pressure is about 630 torr, so I'm going to run a line. So that would be if that line was straight, that would be 650. Well, that'll have to do. And so 625 would be about midway, and I didn't do that very well either. It's harder to write with this stylus than I always expect it to be. We're looking at the line for bromine, number 2. So there's where bromine crosses that line, and that's at about 50 degrees Celsius, or a little above 50. So at 25, what state is bromine still in? It's a liquid. Its vapor pressure is pretty well below atmospheric pressure at that elevation, so it would be a liquid. Number 4 we knocked out because we haven't done that concept this year. So for number 5, we've got systems in equilibrium. If we heat the system, it will shift equilibrium to the right, Or you could also say towards the vapor phase. So it'll shift equilibrium towards the vapor phase. If we increase the volume of the system, it shifts equilibrium left or towards the liquid phase. Everybody gets that. Heating it shifts it to vapor. Anybody a little bit puzzled about increasing volume, shifting it towards liquid? Do you want to talk about that at all? You want to just accept it as a matter of principle and faith, and you don't want to know why or how or anything? Okay, fine. Let's walk through this one. Don't think so. But I have been wrong before. I did this off the top of my head, and I do get these ones confused. Okay, so if we take this, and we increase the volume, we decrease the pressure, because we're not changing the number of molecules or anything. So we would decrease the pressure, so we would decrease the temperature, so it would shift towards liquid. If your notes say that, we'll check them together afterwards.
It says right in the book too.
Really?
Yeah, it's container volume, right?
Increasing container volume shifts it right towards vapor. Why would that be? Okay, well, we'll throw that one out. I hate the increasing and decreasing volumes, and yet I included it on this. Okay. We're going to walk through the logic behind that one again, because that one does always throw me. I apologize. So, for increasing volume, let's get rid of that for right now. We'll talk about it in a little bit. Sigh. So let's look at the chart on the back. This is the triple phase, or triple phase diagram for carbon dioxide. And I love questions like this, where we have a sample of solid CO2. It's at 1 atm, and we put it in an environment where it's 1 atm and 20 Celsius. It was a solid. What phase is it going to enter? So, of course, we take a line from our 20, we take a line from our 1, and that is solidly a gas, which you know CO2 is a gas at room temperature and normal atmospheric pressure. Has anybody here, and what is that transition called? Yeah, I drew that line wrong. Let me fix that. Okay. There. Okay, so that lands it squarely at a gas. And when it's going from a solid to a gas, of course, that's sublimation. So number 6, gas or vapor, doesn't matter which you say, and that process is sublimation. Okay, above what temperature is it impossible to make liquid CO2? So you have to know what point on this gives you that temperature, and that would be the critical point, because that gives you the critical temperature. So if we drop a line straight down from critical point, it looks like about 30 degrees Celsius. So above 30 degrees Celsius, no matter how much you compress it, you can't make it into a liquid. All right, and number 8, if a sample of CO2 has all 3 phases in equilibrium, what conditions of temperature and pressure is it under? So you have to know, and I didn't say what's its triple point, but you have to know that the point where it's in equilibrium with all 3 phases is the triple point. And I was so proud of myself because I carefully, oh, that's not the triple point. Jeez Louise. Undo. There's the triple point. It was a dot. I was so proud of myself for very carefully having, eyeball estimated those conditions, and one of my students in 4th period said, should we just use the ones that are written on the chart? Yes, you should. If it's given to you, then you should use it. It's much more precise. So, of course, triple point conditions for CO2 are negative 56.6 degrees Celsius and 5.11 ATMs. I had negative 50 and 6 ATMs, so I was pretty happy with my eyeball estimation. I didn't think that was terrible. Actually, the pressure's pretty bad, but oh well. We'll take it. It's written on the chart. Use that. Okay, and number 9, what is the minimum pressure necessary to condense a sample of CO2 at room temperature 20 degrees? So let me get rid of a few lines here. Well, I guess I can get rid of all those lines. Okay, so we're going to take a line from our 20. Badly, badly drawn. Okay. Try to get that as straight as possible. And we want the amount of pressure that's going to meet that. Well, that's badly drawn too. As is that. Can I move just this up? Yes, I can. Okay. So we're looking at, and again, this one's a tough one to break down. So that's 90 ATMs between 10 and 100. So that middle would be 10 plus 45. That would be 55. Halfway between the 55 and the 100, so you have 22 plus 55, you've got 70 something, and it looks like it's a little below that. So between 60 and 70 are probably answers that I would take, and I believe on the key I have 60 ATMs. That's honestly probably a little bit shy. I think 65 is a better answer, but we don't have the sig figs to support that. I'd take anything between 60 and 70, honestly. So, questions, comments, concerns? And then we'll walk through the whole increasing, decreasing volumes thing.